Hi, I'm Robert, and I'm going to tell you a bit about challenges in machine learning and the implications for distributed systems, as well as a project called Ray, which is an open source project that we've been developing here at Berkeley. I'm a grad student here at Berkeley. So to start off with, let me give a high-level depiction of the machine learning ecosystem and why distributed computing comes up in the first place. So I'll try to ground this in lessons and ideas you've seen so far in this class. One central theme in machine learning is the concept of machine learning training. You may remember the lesson on multi-class classification or on regression. Both of these are examples of machine learning training. You take some model that may be a linear model or both for regression or the classification, and you try to optimize your model to fit the data. And that optimization procedure is typically done with stochastic gradient descent or some variant of stochastic gradient descent. And why does distributed computing come up? Well, there are a number of different reasons. You may have more data than you can fit on a single machine. These gradient computations used for stochastic gradient descent are often very computationally expensive. So you can often speed up the computation and make it run faster by leveraging multiple GPUs or multiple machines. And here in the stochastic gradient descent equation, you see this summation that's summing over a bunch of data points. Summations are often good candidates for parallelization because they can be executed. They can be decomposed into separate summations that are executed in parallel and then aggregated together. So of course, training is just one part of the machine learning ecosystem in the supervised learning setting. Another sort of emerging area in machine learning is reinforcement learning, which is less concerned about, so supervised learning is more concerned with making individual predictions. Reinforcement learning is more concerned with finding policies or strategies for how to take sequences of actions in changing environments and learning how to do that. And examples of this include learning to play board games like Go, learning to play video games. Board games and video games are very amenable to reinforcement learning because you can simulate them perfectly, whereas and simulation is a key aspect of many reinforcement learning algorithms. But we're also starting to see applications of reinforcement learning to more real-world problems. Here's an example of another simulated environment, but the kind of thing you can do with reinforcement learning. So here we have a simulated humanoid robot, and it's learning to walk or to run by trial and error. And I won't dive into too much detail about reinforcement learning, but at a high level, it learns by trial and error. It gets rewarded for moving forward successfully and gets negative rewards for falling over. And you can see after this is trained using Ray. After some number of iterations, after 500, it learns to run successfully. And so that's one interesting example of a reinforcement learning problem. I'll show you another. So here is this is a simulator of traffic, so of traffic congestion. Here we have a 3-lane road merging into 2 lanes and then into a single lane. And you can see there are red cars and white cars. The white cars are supposed to represent human drivers that are just driving like normal human drivers. The red cars are autonomous vehicles that are coordinating with each other or trying to coordinate together to basically reduce congestion, and by essentially shepherding the traffic in a way that prevents traffic jams from arising. And this is work done by researchers here at Berkeley as well. So these are some of the kinds of things you can do with reinforcement learning. I should say, in terms of distributed and parallel computing, that comes up here because all these simulations are very expensive to run, and so you often need to parallelize the computation over many CPU cores or many machines to get things to run in a reasonable amount of time. So model serving is what you do after you've trained a model. You've trained a model to recognize objects or to translate languages or things like that. And now you want to take your model and use it to actually generate predictions or run some service or make some decisions. And so, for instance, maybe you trained your neural network to translate from English to French, and now you want to use that to run Google Translate. Well, you have a bunch of queries coming in, and you want to respond with the translated version of the sentences, and that's essentially the problem of model serving. And as you can imagine, there are more queries arriving to Google Translate than you can handle with a single machine, and so hence the need for distributed computing. Hyperparameter search is another staple of sort of machine learning pipeline. If you remember this bias variance trade-off slide from a previous lecture, you often have to make many choices when you're modeling a problem. That may be the choice of a regularization coefficient or the function class that you're using to fit some data. And you often don't know which choice is best a priori, so you want to run to try multiple choices and see how they do on some validation set. And that whole process of running this regularization coefficient or the function class can be considered hyperparameters, and the process of trying different ones, often in parallel because running these experiments is expensive, is the process of hyperparameter search. Lastly, data processing. If you're training a model or learning some policy, you're often working with data, and that data often needs to be processed and transformed. So we have tools like the MapReduce abstraction and the MapReduce system, as well as Apache Spark, which you saw from previous slides, can be used to, here it's being used to filter some log files. So data processing is an important part as well. And I won't go into streaming, but you can imagine that data, instead of being a static data set, is actually a streaming data source with data coming in all the time. So that's a bit about the picture today in machine learning. You have all these different components of the machine learning ecosystem, and distributed computing is important for all of them. But and the way that manifests itself is that each of these components today is a standalone, special purpose distributed system. And here are some examples of specific distributed systems that people use to accomplish these tasks. So if you want to do data processing, you might use Spark. If you want to do training, you might use Horovod or distributed TensorFlow. And these are great. These are powerful systems. But this poses a pretty serious challenge for cross-cutting applications that want to do all of these things together. You can imagine that a lot of the kinds of applications people want to build today, you might have some streaming data coming in. You need to transform that data. You need to then incrementally train new models, push those into production and start serving predictions from those models. And of course, there's hyperparameter search in there. So if you want to build that today, you're either stitching together a bunch of these different systems, or you are building a new custom system from scratch. And that's, I'll say more about why that's a challenge and how we're trying to fix that with Ray. But first I'll say more about why we actually need distributed systems. So again, why do we need distributed systems, and why not just do all these things in a single process on your laptop? Well, there are two main reasons. One is there's just too much work to do on your laptop if you want to keep up with all the incoming queries, or from Google Translate, or if you want to train your neural network in a reasonable amount of time. It just goes a lot faster with more machines. And the second thing may be that even if you could do it quickly enough on one laptop, you might not actually be able to fit all the data onto your laptop. And many of these things are actually very data hungry. So what are the different aspects of a distributed system? Well, there's a lot of diversity in the kinds of designs and architectures for distributed systems, but there are many shared components. So at some core level, if you're dividing work among a bunch of CPU cores or among different machines, you need to divide the work into units of work, which we'll call tasks, and decide which tasks get assigned to which machines and which cores on those machines, and when all of these tasks run. If some are going first and some are going later, are there dependencies between these tasks? That process of dividing the work up between the different machines is called scheduling. Of course, you have to also transfer data between these machines, right? If you're dividing up the work, then you need to have some way of communicating and coordinating. These machines can fail, so distributed systems will often deal with failure handling and managing all the different resources on the machine. So what you can imagine, each of these different, like the way TensorFlow handles these 5 challenges and the way that Spark handles these 5 challenges are very different. So if you want to stitch 2 of these things together and have a pipeline that uses Spark for one part and TensorFlow for another and Flink for another, then you're going to have to reconcile different scheduling approaches, different ways of handling failures, and that can be a challenge. So what we're trying to do with Ray is, take all these blue boxes representing distributed systems and remove them, and essentially have a single distributed system layer, which we're calling Ray, and implement all these different components of the machine learning ecosystem as libraries or applications on top of a single distributed system. So in the same way that in an application you might be able to import Python in a Python application you might be able to import NumPy and Pandas and use all those together very easily. We'd like to make it easy to, on top of Ray, import our library for training and our library for data processing and reinforcement learning, and just use these all together. And the underlying system would take care of these different standard distributed systems challenges, and so the applications wouldn't have to worry about that. So again, we're trying to move from this picture where you have special purpose distributed systems to this picture where you have a general purpose distributed system that can support all the other components as libraries or applications on top. And of course, if you want to do that, you're going to need a very general purpose underlying system. And the way that we achieve generality is by essentially, when you're using Python or any programming language, you typically have functions and classes, right? These are 2 very core concepts. And so the way that we achieve a generality in the distributed computing context is by taking these 2 core concepts and providing distributed systems analogs. So functions turn into these remote functions, which are tasks essentially, and classes translate into actors. And I'll elaborate a bit on the Ray API now and what that looks like. So here are our 2 regular Python functions. One of them just creates an array of zeros, and one of them multiplies 2 arrays together. So with Ray, we can take these functions and add the ray.remote decorator. And now when we invoke one of these functions, it immediately, so whereas in regular Python, calling zeros would actually execute the function and wouldn't return until the function finished executing. Here, when we call zeros.remote, that immediately returns an object ID or a future that represents the eventual output and creates a task, essentially a unit of work, which is handed off to the back end and run asynchronously in the background. And because it returns immediately, we can call the function again to create a second task, which also runs in the background. And because this is how futures or object IDs let you achieve parallelism. because we can create the second task before the first one has finished running, they execute in parallel. So now we can create a third task by calling the dot function, and we can pass in the outputs, the object IDs from the first two tasks as arguments into this third task. That creates this, that's encoded in this graph. This graph is the sort of data structure that the backend reasons about. This shows that this third task is dependent on the outputs of the first two tasks. So this third task won't execute until the first two have finished and created their return values. Now, if you actually want to retrieve the output of this whole computation of the dot task, you can call ray.get on this last object ID, which will return the desired output. So now I'll show you what that looks like in Python and how you can use that to parallelize things. So here is a Jupyter notebook. I'm going to import Ray and call ray.init. What this does is it essentially starts up the Ray processes. This is just running on my laptop, but it starts up a scheduler. I'll say more about the architecture and the processes in a little bit. Here's a slow function which just sleeps for half a second. Okay, and now here what we're going to do is we're going to call the slow function 4 times in a loop, and that takes 2 seconds because it's sleeping for half a second and then doing it 4 times. So that's slow, unfortunately. So now let's try to parallelize it using Ray. So I'm going to copy this code and try to speed it up by using Ray. So we're going to take this slow function and make it into a remote function by adding this ray.remote decorator. Now, if I want to call slow function, I have to call slow function.remote because it's a remote function, and this creates a task that will run in the background. Now, if I try just running this, it'll be instant. Oh, I forgot to rerun this. Okay. Now, if I run this, it'll be essentially instantaneous. So it took 260 microseconds. That's because we're submitting all the computation, but we're not waiting for it to finish. So one thing we can try doing is, if you want to actually, so here, if I print x or results, you can see that results are this list of 4 object IDs. Now, that's not what we want. We want the results to actually be the outputs of slow function, which are 1. So, the first thing we could try doing is calling ray.get on this slow function. So how long is that going to take? Well, let's see. So it took 2 seconds. That's the same speed as the original serial version. And the reason for that is that we submitted one task and then waited for it to finish. And then the next time around the loop, we submitted another task, waited for it to finish. So each pass through the loop is taking a full second because we're only running one task at a time. If we want to see what that looks like, we can go to this Chrome tracing and go here. This is the last thing we ran. So you can see that there are 4 tasks, 4 of these calls to slow function, and they're happening one after the other. And so the whole thing in aggregate is taking about 2 seconds. What we want, so here, okay, this is a lot of information to digest, but time is going from the left to the right, and each bar essentially is a worker process that executes tasks. So here we have a single worker which is executing these 4 tasks in a row, and that's not what we want. So now I'll show you how to actually parallelize this using Ray. So let's see. So now let's try, instead of, I'll just get rid of this. So instead of instead of calling ray.get right after we submit the function, we're going to do that at the very end. So we're going to say results equals ray.get of results. So now we're, let's see how long that takes. So that took half a second, and that's good. That's what we want, because we're going through the loop 4 times, and each time we just submit the function, and then at the very end, we wait for all of the separate tasks to finish. And so now if we go and look at what that looks like in the timeline, you can see, oops, this was the last thing to run. Now we have these 4 tasks, and they're vertically stacked, which means they're executing at the same time, right? So time goes from left to right. They're being executed on 4 different workers in parallel. And this ray.get here is the driver application. This is my actual IPython notebook that's waiting in the ray.get call. So this is exactly what we want, and if we measure the time from start to finish, you can see that it's about half a second. Okay, so that's great. Okay, now I'm going to go back to the slides. So what I just showed you was how to take a Python function and execute it asynchronously as a task to achieve parallelism. And note that this can run on multiple cores on the same machine or different machines entirely, and it's the same code. So this is pretty general, but one thing it doesn't do is it doesn't allow mutable state to be shared between multiple tasks. So what if I wanted some global variables that is modified by the zeros task and then by the dot task, and I want those mutations to carry through? Well, that's typically the kind of thing you would use a class for in Python, right? You would have a class sort of encapsulate the state, and the methods of the class would manage updates to the state. So let's do that. Here's a Python class, and it has some value. This is going to be the mutable state, which will initialize to 0. It's just a counter, and we have an increment method which adds 1 to the counter. So how do we do this in the distributed setting? Well, we can add the ray.remote decorator, and now if we created an instance of this class, that creates a new process somewhere in the cluster, and method invocations on this actor handle object turn into tasks that execute on the actor process. So remember, a process is essentially just a program. When I say process, I mean program. It's executing a sequence of instructions. If you start up like Python on your laptop, that's an example of a process. This actor is basically a Python process that is running these tasks, which are these units of work that were, one method invocation, basically. So we can invoke multiple methods. Those will execute serially on the actor, one after the other, to avoid race conditions where you have two things executing concurrently. And they return futures or object IDs like before. And if you want to retrieve the actual values, you can call ray.get. So I'll come back to actors later on in this lecture, and we'll show how you can use actors to implement a basic parameter server example. Okay, so what's actually going on under the hood? Let's go back to this remote function example and just focus on this picture. So we have these 3 tasks, and there's some dependencies between the tasks. So we know how to write the code, right? These are the 4 lines of code that give rise to this. At runtime, when you execute these 3 lines, these tasks are submitted to the backend. But how do they actually get executed? Well, here's a depiction of a cluster of 3 machines. So here, these gray boxes are machines, and these colored boxes inside the machines are processes. So each machine has some blue Python worker processes, which essentially, those are the ones that actually run the Python tasks. We have these object store processes, which store the outputs of the task. And we have these scheduler processes, which make decisions about which tasks run on which workers or on which machines. So now we get this graph, which we want to execute. So the first thing that happens is that these three tasks are given to one of the scheduler processes. Since the actual application is running on some machine, they're handed off to the scheduler that lives on the same machine. So then the scheduler will make decisions about what to do with these tasks. So the first task it will give to, say, one of these workers, and that worker will start executing it. And the second task it might give to another scheduler, which then gives to some worker on that machine. So these two tasks can be executing in parallel on different machines. And this third dot task might just stay put where it is, because it depends on the outputs of the first two tasks, which aren't available yet, and so it won't execute until those outputs are created. So now these two zeros tasks finish executing. They store their results in their local object stores. Now we want to execute this dot task. So this dot task goes to this worker process, is assigned there, it's scheduled there. And now it's missing one of these objects. It's missing object 2. So object 1 is given to the dot task to execute, and object 2 is transferred to this machine where it's needed, and then given to the worker. So the worker now has all the inputs it needs to execute the dot function. And then once the dot function finishes, it stores its output in the object store. So that's the full procedure for what happens when we want to actually execute this program. And one other thing to note is we have this global control store where we store essentially these specifications of the different tasks that have run. And that's important because if a machine fails and we lose some object, that we need to then we need to recreate the object, and we do that by rerunning the task, and the specification of the task is stored here. So that's a bit about the Ray architecture. So now I'll give an example of how to actually implement an example in parallel using Ray. So suppose we want to write a function to determine if a number is prime. So we have some number p. We want a function that returns true if p is prime and false otherwise. And prime again means its only divisors are 1 and itself. So here's an example of one way to do it. It's certainly not the most efficient way. But basically we loop through all the possible divisors of the prime number, and for each possible divisor we compute p mod d, and so that if this equality holds, then that means d divides p, and therefore p is not prime, so we return false. If this equality does not hold for all of the divisors, then we return true because p is prime. And I guess you also have to check some special cases about if p is equal to 1 or something like that, which I omitted. Okay, so that's great, but you can imagine, so this is a serial Python program. It's going to loop through each divisor and test it sequentially. Is there a way we can speed this up and make it parallel? Well, yes. One way to do that is to essentially partition all of the divisors into different groups. So yeah, so one point I want to make is that for loops like this are great candidates for parallelization, because it means there's a bunch of work that's being done that might be possible to do in parallel. Some programming languages, so MATLAB is a good example where it's such a commonly occurring pattern that there's a parallel for loop. So the keyword is par for, and if you use that instead of for, then it does the for loop in parallel. You can't always parallelize for loops because it's possible that each iteration through the for loop requires work that was done in the previous iteration. But for loops are often a good candidate for some expensive computation that might be possible to speed up. So the way we want to speed this up is by taking the divisors, all these, from 2 to p, and chunking them into different ranges. And then we're going to have one task check the divisors from 1 to k, another task check the divisors from k plus 1 to 2k, and so on. And let's see. So if any of these, if we find a single divisor of p in any of these batches, then that means p is not prime. And if they all don't find any divisors, then that means p is prime. So let me show you how to do this in Jupyter. Okay, so here's a helper function which is going to test all the primes from lower to upper, all the divisors from lower to upper, and see if they divide p. If any of them does divide p, will return true, and if none of them divide p, will return false. And we handle some special cases first. So, or rather, we ignore divisors that are 0, 1, or p. Okay, so we're defining this as a remote function, so I can define that. And now here is the actual primality testing, the isPrime function. If we ignore this parallelism argument, then it's essentially just the code we had back here. But if we don't ignore it, then we have this for loop, and within each for loop, we're calling the test divisors. Each pass through the for loop defines a different range of divisors from lower to upper. And then for each pass through the for loop, we are returning the actual, we're invoking a task that checks the divisors in that range. And note that we're calling test divisors.remote, so we're just submitting the task. We're not waiting for it to finish. So after this for loop, we've submitted parallelism number of tasks, and storing the output object IDs in this list. And then we're calling ray.get to wait for them to finish and retrieve their results. So this is going to be a list of booleans, of trues and falses. If any of them is true, if any of them, if all of them are, let's see, if any of them is true, then p is not prime, so we return false because of the not. And if all of them are false, then we return true because none of the divisors divide p. So let's try that, just to test that we wrote the function correctly. So 2 is prime, 3 is prime, 4 is not prime, 5 is prime, 7 is prime, 11 is prime. So this looks correct. Okay, so now let's see if we can speed things up. So let's check if 100 million and 7 is prime. So off the top of my head, I don't know the answer to that, but let's run it. So this is running with parallelism equals 1. That means no parallelism. So it's just submitting one task and waiting for it to finish. So this could take a little while. I think it'll be another 10 seconds. Okay, so it took a total of 16.5 seconds. So now let's try it with parallelism 2. So this means we are submitting 2 tasks and then running them in parallel and waiting for them to finish. So the serial version took 16.5 seconds. The parallel version took 9.7 seconds, so not quite twice as fast. Let's try it with 4, a degree of parallelism equal to 4. So that took 5 seconds and a little bit, so again, not quite 4 times faster. Of course, 4 times faster is the the fastest you could hope for it to speed up. So what if I run it with a degree of parallelism equal to 100 instead of 4? Would we expect it to be 100 times faster? So the answer is it depends. I'm running all of this on my laptop, and my laptop, you know, I think in terms of arithmetic, it only has 4 cores. So no matter what you're doing on my laptop, you shouldn't expect it to go more than 4 times faster. But let's actually try running this and see what happens. And sure enough, takes about 5 seconds. So that did not go much faster than running it with a degree of parallelism equal to 4. If that didn't make sense, you might think about why that might be true. Okay, so that's an example of using Ray and using parallelism to speed up a function that checks if a number is prime. By the way, there are other, like, if you're interested in prime numbers and things like that, there's some really cool algorithms for randomized algorithms for checking if numbers are prime and things like that, which I won't go into now. But you might look up like Fermat's little theorem or Miller-Rabin primality testing. Okay, so now I'll give an example with a tree reduce, and this will show up in this homework assignment, so this is particularly relevant. So if you remember MapReduce from the previous couple lectures, the reduce part of MapReduce is about, the map part is about executing a bunch of tasks in parallel. The reduce part is about aggregating all of those results. And there are many ways of reducing things or aggregating things, right? So one is you could just pull them all to a single machine and then aggregate them serially there. You could do this more fancy tree structure thing, which I'm about to show. There are also, if the thing you're working with is large vectors of numbers and you want to add them together, there are algorithms like ring all reduce and butterfly all reduce and things like that, which are, you know, fast strategies for adding vectors together in certain settings. So yeah, so this is relevant for the next homework assignment. So say we have a bunch of numbers, we have 8 numbers, and we want to add them all together. And for the sake of this exercise, let's assume that we have to add them up pairwise. So we can only add 2 numbers at a time, and adding 2 numbers takes half a second. Obviously, this is a toy example, but if instead of individual integers, if we instead had large vectors, then you know, it could, if it's a gigabyte or something, it could start to take you know, half a second might actually be more realistic. Okay, so it turns out there are a bunch of different ways we can add these numbers together 2 at a time. We can start by creating a task that adds the first 2 numbers and produces some output. And then we can create another task which adds that output with the 3rd number and produces a new output. And then another task which adds that output with the next number and produces an output. And then takes that output and adds 5 and produces an output, and so on, right? So what's going on here? Well, how long is this computation taking? If you look at all of these 7 add tasks that we're running, each one depends on the previous one. So we can't run this second add task until the first one executes, and that's true for all of them. So since each one takes half a second, and there are 7 of them, that means this whole thing is going to take at least 3.5 seconds. So this is an example with no parallelism, right? We're still executing it in the distributed setting. These things might be running on different machines or different cores, but it's not going any faster because we're not exploiting any parallelism. So what's a more clever way to do it? Well, we can do what's called a tree reduction. So we can submit 4 tasks in parallel. The first one adds up the first 2, the second adds up the next 2, and so on. Those all produce their outputs. These can all run in parallel because there are no dependencies between these 4 tasks. Then we can submit 2 more tasks, which the first one adds up the outputs of the first two tasks, and the next one adds up the output of the next two tasks, and those run in parallel. And lastly, we aggregate the final two results and produce our output. So how long did this take? Well, if you look at the sort of critical path, each, this last task depends on two tasks, which depend on these four tasks. And because of the parallelism, this first stage can take half a second, the second stage takes half a second, and this last stage takes half a second. So in total, it can be 1.5 seconds, whereas the previous picture took 3.5 seconds. So that's a big difference. And you can imagine as this number of 8 gets larger and larger, this is going to grow linearly. The time taken by this is linear in the number of things you want to aggregate, and the time taken here is logarithmic in the number of things you want to aggregate. And that's because the depth of this tree is logarithmic, and you may want to think about why that's the case. So what does it actually look like in code? Like, how do you go from this picture to this picture? Well, it turns out it can be just a single line of code difference between the two. So take a look. This first block produces the linear aggregation, and the second block produces the tree aggregation. So here we have these values that we're aggregating. We're looping over this list of values, submitting a task that adds the first two values, and then removing those first two values from this list of values, and adding the new value. And the only difference between these two blocks of code is how we're adding the new value. We're either adding it to the front, the same place that we popped off the first two values. That's what's giving rise to the linear reduction. And in the second case, we are appending it to the back of the list. So we're popping from the front, aggregating, and appending it to the back of the list. And that's giving rise to the tree reduction pattern. So that's would probably take a little bit of thought to digest that and figure out why it's true. But you may be interested in just running this code and seeing that for yourself. So I'll show you that in the Jupyter notebook, and you'll see this more on your homework assignment. Okay, so here I'm using 16 values instead of 8. And let's see. So this is the first approach. I'm running this block now, and it's still running. And so that took, let's see. So each add call takes half a second, and because we're aggregating 16 things, we have to call add 15 times. If we do them serially, like this approach where we append to the front, then you have 15 serial tasks that take half a second, so that's going to be 7.5 seconds. Now if we look at that in the timeline, what does that look like? So here's the most recent thing we ran. So here we have, I believe that should be 4, 5, 6. That should be 15 tasks. Yeah, that's 15. And they're happening serially. So yes, they're being executed by two different workers because we have two different rows here. But you can see that the second one doesn't start until the first one has finished. And this whole thing is taking 15.5 seconds. If you can see 7.5 seconds. Okay, so now what if we do it in a different way? So just to show you, I'm copying. It's exactly the same code, except all I'm doing is removing the append from the front and appending it to the back instead, and that'll do a tree reduction. So now if I run that, it took 2 seconds. So now if we look at the timeline for that, here's the thing I just ran. So you can see that okay, it doesn't really look like a tree, but first we have 8 tasks executing in parallel, and that's taking half a second to run all 8 of those. Then we have 4 tasks executing in parallel. It's taking another half second to execute those. Then we have 2 tasks executing in parallel, and finally 1 task executing by itself. So in total, this is taking 2 seconds, which is much, much faster than the 7.5 seconds. So this is just almost the same code, but a slight change can expose different degrees of parallelism. So that's a fun example. You'll see more of this in the assignment. Okay, so lastly, I'm going to show you a parameter server example, and this is fun. This uses actors, and this actually gets at some really interesting patterns in machine learning training. So if you remember the regression setting, you have a bunch of data points, and you want to find the model that fits the data the best. And here the model is this line, which is a linear model. This picture in the defines sort of the problem setup, right? You have this is an optimization problem because you're trying to find the model that fits the data the best. So if you can quantify what fit means, then if you can quantify the error, then you can try to minimize the error. And the optimization algorithm of choice is often stochastic gradient descent, and we are essentially repeatedly, we randomly initialize some line, and then you iteratively improve the line by moving it in the direction of steepest descent of the loss function. And here, this summation is the thing that we're going to parallelize. So there are many different ways of doing this, but a common pattern is actually called a parameter server. So how are we going to parallelize this summation, right? So we want to compute a gradient over a batch of data. Well, we're going to do that by taking our batch of data and partitioning it up among several worker processes. Each of these workers are going to compute the gradient for their separate batch of data, and then we're going to add the gradients from all the workers together to get the sum. And you can imagine doing this by having a parameter server actor. So a parameter server, here it's really just it's just a process that holds the parameters of the model. So here parameters essentially mean like the coefficients of the linear model, like the slope and the bias. If it's a neural network, it could be like the weights of the convolution or the matrices in the neural net. So we can have all the workers compute their gradient and then send them to the parameter server to get added together. That updates the model, which is stored in the parameter server, and then the new model gets sent back. So it could look something like this. Workers send gradients to the parameter server sends parameters back to the worker. And that's why it's called a parameter server, because it's serving parameters to the workers. So this is a common thing to do. However, as you can see from this picture, sometimes the parameter server can become a bottleneck because you have all these different workers that are talking to the parameter server. And there are different ways it can be a bottleneck, but it's often if these are on different machines, it's often the network bandwidth into and out of the parameter server machine. So one way to address this is to split your parameters across multiple parameter servers. So here, if your parameters are a vector of length 1,000, or say length 3,000, then each parameter server could have a disjoint subset of the parameters. So each might be responsible for 1/3 of the parameters. And then when a worker computes a gradient, it partitions that gradient into 3 pieces, sends each piece to the relevant parameter server, and then those results are aggregated, and then each parameter server sends all of its parameters to each worker. So let me show you what that looks like in Python. Okay, so here's a parameter server class. This is a regular Python class. It has a vector of zeros, which are the parameters. It has a method for getting the parameters, which just returns the vector. and a method for updating the parameters, which essentially adds the gradient to the internal vector. And we're going to use Ray to make this a remote class or an actor. And now we're going to instantiate an object, an instance of this class by calling parameter server.remote. And now we can call the getParams method to actually see what they look like. And if we call this multiple times, it's just a vector of zeros because that's how the parameters were initialized. Okay, now we can update the parameters. So here I'm calling update params twice and passing in a vector of 1s. Now what happens if we get the parameters? Well, now it's a vector of 2s, and that's because this state, this self.params vector, is shared and mutated by all of these tasks that are executing on the parameter server. So yeah, if you can see, if I run that again, now it's a vector of 2s. I can run this again and run this again. Now it's a vector of 4s because we updated it 4 times. Okay, so that's what I've showed you so far is this parameter server part. I just created one of them, so we have this picture. But now how do we create these workers? Well, here is a function, a remote function, which takes in a handle to this parameter server, and it loops around and does 3 things. First, it gets the latest parameters by calling ps.getParams and ray.get. Then it computes a gradient update. And here I'm just making up a vector of 1s, but in the real application, this would be where you use TensorFlow or PyTorch and some data that you have locally to actually compute a gradient update. And then we're sending that update back to the parameter server by calling ps.updateParams.remote. And you can imagine if you have a collection of parameter servers instead of just one, then you get the parameters from all of the parameter servers, and you send the relevant update to each different parameter server. So now we'll define that function. And now we can start 3 different parameter servers. And so we created 3 processes, 3 of these workers that are running in parallel and talking back and forth with the parameter server. They're sending updates, getting the latest parameters, sending updates, getting the latest parameters. And now if we get the latest parameters, you can see that it's 100. Run it again, now it's 112. So things are updating in the background, and you can see that because they're being mutated. So that's really exciting. Basically, we've taken this picture or this picture. A parameter server is something that's typically implemented with a standalone code base and shipped as an executable, kind of like a database. And it's not that customizable, right? Because you have this big C++ code base implementing a parameter server. But here, because we implemented it ourselves in a few lines of Python, if you want to change the way the update rule works, instead of addition, you want to use some other kind of optimization algorithm, that's fine. If you want to shard your parameters across multiple parameter servers, we can just start multiple copies, multiple parameter servers. Like I can say ps1 equals parameter server dot remote ps2. Like this creates 2 parameter servers. If you want to wire them up differently or handle stragglers differently, these are all a couple lines of code you can change in the actual application. So this is what I mean by taking things that used to be distributed systems, like a parameter server, and implementing them as libraries or applications on top of Ray. So that's the parameter server example. And there will be another example in your homework assignment that uses actors to do something similar. So I want to point out that Ray is open source. It's a project that we're developing here at Berkeley. And it's something you can install and try out. It's sort of trying to enable this trend of moving from special purpose distributed systems toward a general purpose distributed system. And trying to unify all the different aspects of the machine learning ecosystem that you've seen so far in this class. So things like training, things like hyperparameter search, things like data processing. Those are things that we're trying to make possible to do in a unified way on top of a single system. So that's all. Thanks a lot.